So I'm going to introduce the types of bonding, and we're going to get into molecular geometry in this video. So this is really important. Take your time. If you need to stop it to listen again, but by the time I'm done, you should be able to build your own molecules. So quick review, it's that electronegativity difference that controls the type of bonding. So we're done with the idea of ionic bonding, where you have a large difference in electronegativity. Now we're looking at no difference or a smaller difference that leads to either a nonpolar covalent bond or a polar covalent bond, but a covalent bond, a sharing of electrons. The electronegativity differences are determined by the size, so your nonmetals have much smaller radii than your metals. So you're looking at elements over in this area that are bonding together. Your ionic character is defined as 50%. So you have an ionic bond if you have 50% ionic character, which is always, if you look at these that are 50% and above, are ionic, and then below that you have covalent bonding. That covalent bond is really a fighting for electrons. We call it a sharing, but really this nucleus wants this electron and it wants its own, and this nucleus wants this electron and wants its own. So they pull the two nuclei together, and it's that overlapping of those orbitals that causes that bond. So you're looking at nonmetal elements creating these covalent compounds because of small differences in their electronegativity. The properties of covalent compounds, again made from two or more nonmetals, they're sharing those electrons. They have much lower melting points than ionic compounds, and they are often liquids and gases. They can be solids, but with very low melting points, where ionic have very high melting points, high boiling points, and strong bonds, and are always solids at room temperature. So covalent compounds are pretty much the opposite. So that covalent bond forms, we'll look at two hydrogen atoms, as they start pulling their nuclei together to try to steal the electrons out of each other's orbital. They reach that optimal distance where they each believe they have custody of the pair of electrons, and that forms the H2 molecule. And when we draw that line, this is what we're drawing. That represents those shared pair of electrons that they each think they have. They think they have two electrons. They think they have two electrons. So your Lewis dot is a simple structure to show that overlap of orbitals. Those orbitals form when the atoms get close enough to interact. So if they're far enough away, they can't interact at all. As they get closer, their energy drops as they become more stable in trying to share those electrons until they get to that optimum distance. If you try to push them closer together, they start to repel. But there's an optimal distance where they have the perfect bond length overlap of orbitals, and that's at that minimum energy. So this is that perfect overlap of orbitals. All of your bonds will form so that they have that distance that provides them with minimal energy and greater stability. So a nonpolar bond, so still looking at simple hydrogen, hydrogen has a nonpolar bond because the atoms are sharing their electrons equally. There's no difference in electronegativity. This is called a ball and stick model, and this is called a space fill model. Your nuclei are somewhere in the center here. So this is more of the reality, but of course when we are drawing our structures and building them, we're going to show that overlap of orbitals with a stick that will help us with our geometry. So no difference in electronegativity. A polar bond has a difference in electronegativity between the two atoms, and you will have a partial negative charge on the more electronegative end and a partial positive charge on the less electronegative end. You have a difference in electronegativity. The electrons spend a little more time around the chlorine than the hydrogen because it pulls the electron cloud towards it, distorting that electron cloud and giving you a polar bond. That means a positive end and a negative end. Now, they're only partial positives and negatives, but they are positive and negative ends. So there's your ball and stick. Your more electronegative element has the partial negative charge, while the least electronegative has the partial positive charge. Polar bonds and nonpolar bonds. We also call polar bonds dipoles. Di meaning two poles. Two poles is a dipole or a polar bond. So, nonpolar covalent bond, atoms are shared equally, identical atoms. If you do not have identical atoms, you will not be sharing that electron cloud equally. So that will be considered a polar bond. The charges will be on the ends of the more and least electronegative elements, partial charges or dipoles. An unequal sharing of those electrons. So bond polarity is due to differences in electronegativity, and this is the more extreme, and we're now just dealing with these. So now you should be able to look at a chemical formula and determine the bonding. A transfer of electrons for ionics start with a metal. If you start with a nonmetal and you have two different atoms in there, that's an unequal sharing, so that bond is polar. If the atoms are equal and both nonmetals, then a nonpolar. So let's get to where we left off. You had to learn to draw your electron dot or your Lewis dot diagrams in order to begin to build your molecules. The electrons distribute themselves throughout the atom so that they stabilize every atom in the compound with either an octet or, for hydrogen, a duet. So in the beginning, a lot of you were just putting carbon with 3 oxygens, and of course that would be breaking the octet rule around carbon. For all of your elements other than hydrogen, and you'll learn in a minute boron, you have to at least obey the octet rule. For some of them, you can break it, but that doesn't mean you can add fewer electrons. You have to have an octet. So if that is not something you've mastered, it's going to hurt you a little bit as you move along into building your structures, but you'll eventually get it straight because you'll have to keep practicing it. So your rules: sum up all your valence electrons. They are now going to be distributed among that entire molecule. They don't stay with the atoms they came with. They're distributed to all of the atoms to make everyone happy in that molecule. Form single bonds and follow the octet and duet rules. For hydrogen, you have only an s orbital, so you can only put 2 electrons, 1 bond. And for carbon, nitrogen, oxygen, and fluorine, in that second period, you have only s and p orbitals, so you cannot have any extra electrons. So these always obey their rules, the octet rule and the duet rule. Do not form multiple bonds unless you cannot get the structure to work with single bonds. Multiple bonds have more energy and are highly unstable and would not naturally form. So the only reason you have to use multiple bonds is that when you use single bonds, you don't have enough electrons to distribute. So that means you need to share more effectively. So you're sharing between the atoms with multiple bonds. Now let's get to the exceptions. Boron is the only other element that does not want an octet. Hydrogen does not and cannot. Boron, however, does have p orbitals, but it does not want 8 electrons. It wants only 6. And the reason for this has to do with formal charge. And I told you before, those of you that were putting all those multiple bonds around sulfur, you were looking on the internet, you were looking at structures, and they were giving you structures that follow formal charge rules. You don't know what formal charge is, and you're not going to learn it in chemistry this year. If you move on to AP and college chemistry, you certainly will. But for now, it's a memorization that boron prefers to have only 6 valence electrons. That is where it is more stable. That's the only exception to fewer other than hydrogen. Now you have elements that can hold more electrons. So if you're down here, and we're not looking at any of the metals here, so if you're in the third row, any of these nonmetals in here, not looking at noble gases, although I do have some noble gas compounds that I make for you, and they do have d orbitals. But remember, this is the third energy level. And in the third energy level, here's your first 3D. So if you're in the third energy level, even though you're not putting electrons into your d orbitals, they are there, and they can hold extra electrons. So third row elements and larger, further down the third row, can exceed the octet rule if you need to. Now, you will need to, and they will have to be the central atom. But that being the case, if you count up and you have obeyed the octet rule and you have extra electrons, this is not like a multiple bond when you've used too many. Now you have too many electrons, you need to put them somewhere. So if that central atom is any of these, then you can put those extra electrons. And if we give you some noble gas compounds, which we have been able to synthesize some, so I gave you some examples, then you can put extra electrons there. But you don't just go doing it unless you have to. So if we were looking at SEF4, we count up our 34 electrons. We put our 4 hydrogens, we count all our valence electrons, that would be 32 electrons. We have 34. So we have to be able to put those extra electrons on the central atom, and you can put them in any location, just put them as a pair, and your Lewis dot structure is correct. When you go to build this and you're counting up, you will count that as a lone pair and these as bonding pairs, and that will control your geometry. So, review of rules. Get all your valence electrons. Make single bonds. Follow the rules. These always obey the rules. Don't make multiple bonds unless you need to. Then, boron. Only wants 3 bonds around it. Give it that, move on. Third row and larger elements will often satisfy the octet rule, but they can exceed the rule by using their empty d orbitals. If your central atom has to have extra electrons, check to see where it is located, and it would have to be in the third row or below, and you can put those central atoms, you can add extra electrons to them if necessary. So now let's take these Lewis dot into VSEPR model. VSEPR stands for valence shell electron pair repulsion. And no, we know this word would not be pronounced VSEPR, but that's what every chemist calls it. So it's the valence shell electrons that are bonding, and those electron pairs will repel each other to create a geometry. So the Lewis dot structure is the blueprint for what is happening. So here would be the Lewis dot structure for C2H4. You've got your hydrogen 1s orbitals overlapping the p orbitals in carbon, forming this bond and creating this molecule that you would build. So your Lewis dot structure is how you are going to decide what this molecular structure, or we can call it molecular shape or molecular geometry. They're all the same idea. It's the overlap of those outer orbitals, those valence electrons, that give us these molecular shapes, molecular geometries. So the arrangement of those valence electrons around the central atom is what gives you that. So the geometry is by looking at the atoms that are bonded to that central atom and their ability to attach to that central atom by favorable overlap of orbitals, but then they will want to repel each other to stay as far away as possible, and this will give you that VSEPR shape. Valence shell electron pair repulsion. It's the electron pairs in these outer orbitals repelling each other while still being attracted to the central atom that will give you that geometry. So the bonding pairs try to get as far away from each other as possible to minimize their repulsion and still have the greatest force of attraction for the central atom. So a structure will form that balances those attractive and repulsive forces. These are your attractive forces, and these are your repulsive forces between the two atoms that are bonded to that central atom. Valence shell, electron pair repulsion, predicts three-dimensional geometry by attaching the outer electrons to the central atom in one part of the structure and repelling those lone pairs of electrons away from the outer, giving you the angles of those bonds. Don't forget, it's the central atom that controls where the others bond.
A central atom is determined principally by minimizing electron pair repulsions. Two bonding electron pairs around the central atom result in a linear structure. Carbon dioxide has a linear structure. The bond angle for a linear arrangement is 180 degrees. Three bonding electron pairs around the central atom result in a trigonal planar structure. Boron trifluoride has a trigonal planar structure. The bond angles in a trigonal planar arrangement are 120 degrees. When one of the three electron pairs surrounding the central atom is a non-bonding pair, as in sulfur dioxide, the resulting structure is known as bent. Four bonding electron pairs around the central atom result in a tetrahedral structure. Methane has a tetrahedral structure. The bond angles in a tetrahedral arrangement are 109.5 degrees. When one of the four electron pairs surrounding the central atom is a non-bonding pair, as in ammonia, the resulting structure is known as trigonal pyramidal. When two of the four electron pairs surrounding the central atom are non-bonding pairs, as in water, the resulting structure is known as bent. Five bonding electron pairs around the central atom result in a trigonal bipyramidal structure. Phosphorus pentafluoride has a trigonal bipyramidal structure. The bond angles in a trigonal bipyramidal arrangement are 90 degrees and 120 degrees. When one of the five electron pairs surrounding the central atom is a non-bonding pair, as in sulfur tetrafluoride, the resulting structure is known as seesaw. When two of five electron pairs surrounding the central atom are non-bonding pairs, as in chlorine trifluoride, the resulting structure is known as T-shaped. When three of five electron pairs surrounding the central atom are non-bonding pairs, as in xenon difluoride, the resulting structure is known as linear. Lone pairs of electrons take equatorial positions preferentially. Six bonding electron pairs around the central atom result in an octahedral structure. Sulfur hexafluoride has an octahedral structure. The bond angles in an octahedral arrangement are 90 degrees. When one of the six electron pairs surrounding the central atom is a non-bonding pair, as in bromine pentafluoride, the resulting structure is known as square pyramidal. When two of the six electron pairs surrounding the central atom are non-bonding pairs, as in xenon tetrafluoride, the resulting structure is known as square planar.
So that looks pretty complicated, but you will be given your lab sheet for this, and it will have all of these geometries given to you so that you can look at it when you're building your structures. And eventually, with enough practice, you will memorize them. First, let's make sure that you understand the simplest molecules, having only two atoms, would have to be linear. So when you're following some of these rules about non-bonding pairs, you notice she talked about the lone pairs. This isn't going to work for you following those rules, if you only have two atoms in space will be linear. Now, they may have a nonpolar bond or a polar bond, but they are linear. They're a straight line. Two atoms in space will be a straight line. So it doesn't matter about those lone pairs. There are no central atoms here. VSEPR and all of those rules were looking at when you have a central atom with other atoms coming off of that. If you only have two atoms in space, then they have to be bonded with a linear structure. So let's go through what we're looking at. So total effective electron pairs means the total pairs around that atom, bonding and non-bonding or lone pairs. So if you have two pairs and both of them are bonding and none of them are lone, then you're going to have a linear molecular shape. Let's move up to 3. If you have 3 effective pairs and all 3 of them are bonded and none of them are lone pairs, you will be trigonal planar. That will be, again, 3 bonding atoms and none of them, okay, are lone pairs. That will give you trigonal planar. If you have 3 bonding effective pairs around the central atom, okay, so you have 3 around the central atom, okay. So if they're all bonding pairs, you make that a little more central there, then you're going to have trigonal planar. If one of them is a non-bonding pair and a lone pair, then this structure is going to be bent. The name of your molecular shape comes from the atoms that are bonded on them. 4 with no lone pairs will be a tetrahedral. Now, if you were drawing a Lewis dot structure for CH4, I'm just going to draw the 4 bonds, and we'll assume the hydrogens are on the end of them. That looks like a flat molecule with 90-degree bond angles, but it absolutely is not. The way that you draw your Lewis dot structure is not going to be your 3-dimensional. So you would draw this, and then you would go look. You've got around the central atom 4 bonding pairs. None of them are lone pairs. So they would arrange themselves as a 3-dimensional tetrahedral. That would give them a bond angle of 109.5. These are going to repel themselves into a shape that gives them the greatest distance, and the flat shape is not it. So the tetrahedral shape comes from the repulsion of those lone pairs. Your Lewis dot structure will be flat. It will look flat. It will simply be the blueprint for what you build. So if you've got 4 total pairs and 3 of them are bonding and 1 is a lone pair, we call that trigonal pyramidal. If you have 4 and 2 of them are bonding and 2 are lone pairs, that's bent. So these are off of atoms that have to obey the octet rule in here. Now let's start exceeding that octet rule. 5 total effective pairs with all of them bonding is a trigonal bipyramidal. Now I'm going to show you some of these structures on a computer program that you're going to use to build these as well. 5 with 1 lone pair and 4 of them bonded becomes a seesaw structure, and you will see later that it's going to look very much like a seesaw. 5 with 3 bonded and 2 lone pairs is called T-shaped, and it will look very much like a T. And then 5 with only 2 bonding pairs and 3 of them lone will be another linear molecule. So let's break the rule with even more. With 6 total effective pairs, which is the most that you will have, if they're all bonded, you have an octahedral shape. If one of them is a lone pair and the other 5 are bonded, that's called a square pyramidal. If 4 of them are bonded and 2 of them are lone pair, that's going to become square planar. If 3 of them are bonded and 3 of them are lone pairs, that is going to be T-shaped. And then if you only have 2 bonded and the rest are lone pairs, then you're going to have a linear shape. This should mean, this should be a 4 right there, not a 1. 4 lone pairs. Otherwise, you don't add up to 6. So fix that. Hopefully it's fixed on your sheet. So let's look at this structure. If you were counting up to build this, and you're looking at the central atom, so it's the number of bonding sites around that central atom, the number of effective pairs. So what counts as an effective pair? Well, a single bond counts as one effective pair of electrons. It's a shared pair. The lone pair counts as one effective pair. It's a non-bonding pair. And the multiple bond counts as only one effective pair. It is not counted as 2 because then that would mess up your geometry. It's in the same space, so we are including it as one effective pair. So when you're counting up effective pairs around your central atom, to use your sheet, you're going to say 1, 2, 3. 1, 2, 3. 3 effective pairs. So let's look at our sheet. So if we drew the Lewis dot structure and we counted up 3 effective pairs, we'd look at our sheet. We've got 3 effective pairs. 2 of them are bonding and 1 of them is lone, and it is a bent structure. Now this student drew it as bent. There's no reason for you to draw that as bent. You absolutely could just draw this straight out with your oxygens on it. Go ahead and do that. Let me put my lone pairs up here. 1 there and 1 there. Put another one there. So that would be fine. I'm not going to draw the outer electrons. The outer electrons are not the electrons we're talking about when we count up these effective pairs. We're looking at only what's around that central atom. So it doesn't matter that you drew this bent. It has nothing to do. Your Lewis dot structure isn't your geometry. You would still count up 1, 2, 3. You'd look at your chart, 2 of them are bonding, 1 is lone, it's bent. You write the word bent for the molecular shape. Your Lewis dot structure does not have to be drawn bent. You can if you want to, it's simply not necessary. So that would be your geometry. If you follow the rules, the geometry is the last thing that comes from the structure. What a lot of students try to do is tinker toy their molecules together. It doesn't work that way. Draw the Lewis dot structure, count up 1, 2, 3 effective pairs, look on your little cheat sheet, 3 effective pairs with 2 of them bonding, 1 of them lone is bent. Then build your molecule. This is just your Lewis dot structure. You will be building molecules and you'll be building them on the computer and with your ball and stick gumdrop models. So if you're building these, this is what we would expect to see. I would expect to see a Lewis dot structure. You would have looked on your cheat sheet and you would have built me a bent structure. Notice the student did a good job. The sulfur atom is a different color than the 2 oxygens and they're the same. They're using a gumdrop and marshmallows. You can do anything, toothpicks holding these together. If you absolutely cannot get any gumdrops, toothpicks, marshmallows, you can't get to the store, I still expect some 3D molecules built. You can do it with little wads of paper or clay or any kind of sticks, but you do have to build some for me. So let's move forward. So if this was our regular class, I'd say, here's your kit and here's how we use it. But you don't have a kit. Now you can order one online, and there are quite a few out there. I actually ordered one to make my next video for you when I go over what your molecules should look like. But I only paid $12 for mine, but I do not want you to buy a kit. You can easily use things that you have at home. So here are some samples of gumdrop molecules that I've had students build before for bonus. So they would build them at home if they were sick or something along the line. I've hidden the identities of them, so you can't just copy them, and some of them are wrong anyway. But let's look at the ozone that we have here, and let's determine if this is the correct structure for ozone. You can see they're showing 2 toothpicks for that multiple bond, and then they've got a single bond, and they've got a linear structure. So let's look at this. So if we drew ozone's Lewis dot, which a lot of you did, and you did it correctly after you looked at the answer key, it's got one double bond and one single bond. And you probably drew it in a straight line because there's no reason not to. Then, if you built this, I would agree with you. It looks like what you drew, but you have no lone pairs up here. What do you think these lone pairs of electrons do? They're going to move and repel these bonds away from each other so that they are not going to have this 180-degree bond angle. If these weren't here, you'd have a 180. But with this negative charge field up here, it's going to squish these bonds away from it, and it's going to change that bond angle into a bent molecule. So you draw your Lewis dot structure and you look on your sheet. These are the total effective pairs. You've got 3 of them. One, remember this counts as 1. That counts as 1. 1, 2, 3 effective pairs. 2 of them are bonded. 1 of them is a lone pair. That should be a bent structure. So I will want you to build it as bent. So I will look at your Lewis dot structure and I will see that your molecule supports that. If you wanted to draw your Lewis dot as bent, that's perfectly fine, but it absolutely doesn't change the molecular structure and isn't necessary at all. So here are some molecules that students have done. Notice that when you get more complicated, you may not be able to see, although you can see the shadow behind it. This is a tetrahedral. It's not flat, okay? It is tetrahedral. And if you have a bonding kit, of course, the bond angles are built into the kit, so you get a nice, pretty 109.5-degree bond angle. It's going to be difficult to get those with these other structures, but it is possible. Okay? And you can use marshmallows as well. And you can build fancier molecules if you feel like it. But let's look at what you're going to be doing. See, this is the only homework you will have for the week aside from the assessment, is to complete both pages on this lab sheet and submit to me pictures of the completed lab sheet and your molecules. So let's do CO2 together. If you count up your 16 electrons, and the reason for having already drawn your homework, you've already drawn most of these, so you can go back and see if they were correct. Please don't draw incorrect Lewis dot structures. So you should have corrected them from the last one, so you're not really creating any new Lewis dot structures. There may be a few different, okay? Then to determine your molecular shape, this is what you'll look at, and you will have a handout with this, total effective pairs. So let's look. Around that carbon, you have 1 just around the central atom. So where students really mess up is they start counting all these electrons. It's only the effective pairs around that central atom, and the multiple bonds count 1 time, so you have 2 effective pairs. Both of them are bonding pairs. So that means you have a linear molecule. So write the word linear in the shape, okay, and then build it for me. So I'd like to see your picture to include your structure as well, but you could build it off to the side, or you could place it over here as long as it gets in the picture, or you could build all of these on paper and write underneath of them what they are. The polarity of the molecule I'm going to describe in more detail once I give you directions to this. If you look at this molecule, these 2 atoms are exactly the same. While it's a polar bond here and a polar bond here, the atoms in space are symmetrically distributed. So this is a non-polar molecule. So I'm going to give you some instructions on that, but that would be the last thing you would fill in. So it's draw the Lewis dot, look at the handout that you'll be given, decide on the shape, and then build that shape. So You probably can build with your gumdrops and toothpicks down to there. You are free to build any of these with them as well. It's going to be a little difficult. These are going to be breaking the octet rule. It's pretty hard to get those gumdrops to hold those toothpicks at the right angle. But through number 14, I want to see a gumdrop molecule. For the rest of them, and for all of them, you will then use the computer program that is linked on Schoology. And it looks like this, okay? So when you click on that, let me go back and get my, I need to get my arrow options. Okay, so we're gonna click, and this will come up. Okay, and you're free to look at real molecules. That's fine. They're fun to look at and you can learn a lot. But what I want you to do is to focus on the models. So when you click on this, it's going to bring up electronic structure. And I'm going to take off all the atoms that are on it. So it's got a central atom. So you want to click that you want it to tell you the molecular geometry. Do not ask for the electronic geometry. That will really just confuse you at this point. So you want to know the molecular structure and the bond angles. So let's go ahead and add 2 bonds. So if we had 2 bonds, and you can see that these things will repel each other. Bonds do wiggle a little bit, but they will take that stable 180 degrees. Now let's stop a minute. If this was your central atom and you only had 2 bonds here, you would absolutely be breaking the octet rule. So that cannot be the case, okay? But you could, so let's take those off. And if you replace them with 2 double bonds like carbon dioxide, notice that that's still going to give you that linear shape. Those multiple bonds are not located in space in a different place. They're not moving those atoms around. So there's your linear carbon dioxide, and it will give you your bond angles. So let's take those off, and let's put 3 bonds on. Your 3 bonds would be, right now, you'd be breaking the octet rule with 2, 4, 6 electrons. But this could be boron. So boron, remember, likes to have a trigonal planar geometry with only 6 electrons. But I better not see you drawing this for any other structure because you would be breaking the rule. However, you could replace one of those with a double bond, and now you're not breaking that octet rule. You have 2, 4, 6, 8 pairs of electrons, but only 1, 2, 3 effective pairs. So now your geometry would be fine for something like carbonate ion or sulfur trioxide or something like that. Okay, so let's take that off and let's go, let's add 4. So remember, it said 4 effective pairs around the central atom will be a tetrahedral. It will not be a flat molecule. If you remove one of those and replace it with a lone pair, so remember, if you're going to replace it, you can't just leave that lone pair off. That would not give you the correct structure with the lone pair. So if you're obeying the octet rule and one of them is a lone pair, the geometry becomes trigonal pyramidal. Remove another bond and replace it with 2 lone pairs, and that gives you your bent geometry. Okay? So tetrahedral with 2 lone pairs is bent. Tetrahedral with 1 lone pair is trigonal pyramidal. And tetrahedral with all 4 bonding sites, is tetrahedral. So now let's add 5 bonds. That's your trigonal bipyramidal. If you notice, you've got a 3-sided pyramid in the center. So what you really have are 2 pyramids stacked top and bottom if you're a good 3D visualizer. So that is why it's called trigonal, 3-sided pyramid, bipyramidal, 2 pyramids stacked top and bottom. Okay? Notice, okay, that if we take away one of those bonds and add a lone pair, so take away one of those and add a lone pair, then our trigonal bipyramidal is still 5 bonding sites, but one of them is a lone pair, and that gives you that seesaw molecule. You can sort of see the seesaw right here as you've got the legs to the seesaw and the seesaw. If you had removed another atom and had two lone pairs, so let's put a bond in there, 5 bonds, okay, and take away one, add another lone pair, and take away. So now we've got 5 bonds. 2 of them are lone pairs. And notice they call this T-shaped. And there's a reason for that, because it looks like a T. Okay? So when you play with this, if you build it according to your Lewis dot, the shape is going to show up for you. You don't have to build the shape will come. So let's get rid of all of these right now, and let's go to the octahedral, which is 1, 2, 3, 4, 5, 6 bonding sites. So if you have 6 bonding sites with all bonded, it's called an octahedral. If you replace one of those with a lone pair, it becomes a square pyramidal. Let me try to get it. So here you have a square base with a pyramid, so it's square pyramidal. Remember, only the atoms control the shape. The lone pairs control that bond angle, but the shape is named after where the atoms are located. So if we replace another atom with a lone pair, why I keep doing that? So we've got, take away 1 and replace it with a lone pair. So now we've got 6 atoms, or 6 bonding sites in space, but 4 of them are bonded and 2 are lone. And if you'll look on your lab sheet that you copy out, that's going to be square, planar. It's square, planar means flat. Okay? And then if you took away 1 more and added 1 more, that would give you, again, a T-shaped. And if you removed 1 more bond and replaced it with a lone pair, you would have a linear molecule. So your basic shapes are going to be built around that central atom, and you have as much time to practice on this and master this as you need. So you can, what I want from you with this program, when you start building your more advanced, I want a screenshot of your molecule for each of those that you build. So you can combine all of those screenshots into one PDF document. You should know how to take a screenshot, put it into Word, turn it to a PDF. These are not difficult things to do. Your computer skills need to improve, and then send that to me. So for all of your advanced molecules, you need to make sure you have your screenshots of these, and you should build your simple molecules with these as well. So when you're deciding on your molecule being polar or non-polar, you are looking at the distribution of those atoms around that central atom. And if they're symmetrically distributed, then they are non-polar. So if you have bonds that are polar, because the atoms are different, but those bonds are equally distributed around the central atom, they're symmetrical, then those dipoles or those bond poles will cancel out and your molecule will be nonpolar. Your electron cloud will be evenly distributed. If you have a lone pair that is not balanced, then you're going to have a non-symmetrical molecule, and you will be polar. Those dipoles, those polarities, will not cancel out. Okay? So even though the bond between carbon and oxygen, both bonds are polar, because there are no lone pairs, and these are 180 degrees apart, the entire molecule is non-polar. A tetrahedral structure with all of these atoms being the same will be non-polar. If you had a tetrahedral structure with a different atom, then those electrons are not going to be shared equally around that molecule. They're going to be pulled towards that end of the molecule, so it's not a symmetrical structure. It will have a positive and negative end. The molecule would be polar. So that's a nonpolar molecule, but with the lone pairs, it would become polar. So let's go back and look again at our shapes. Okay, sorry. So if we build our molecule, so let's go ahead and build a tetrahedral. Right now, you have a perfectly symmetrical molecule. This would be a nonpolar molecule. If you removed one of those and replaced it with a lone pair, you can see that your bonds are squished down here. This is no longer symmetrical. You have all this negative charge up here. Trigonal pyramidal, which is your geometry, is always polar. If you replaced with two lone pairs, now you have a bent molecule. It is no longer symmetrical. Your atoms are no longer symmetrical. So it's where your atoms are located in space. If they are not located in a symmetrical position in space, then the molecule is polar. Okay? So anytime you have bent or anytime you have trigonal pyramidal, you are polar, but tetrahedral is nonpolar. So let's jump all the way up, let me add them, to 5. So there's your trigonal bipyramidal. Very symmetrical in space, nonpolar. Take away a bond and replace it with a lone pair. There's your seesaw geometry. Your atoms are no longer symmetrically arranged in space. That is a polar molecule. Take another one off and replace it with a lone pair. So you should have two lone pairs. You now have this T-shaped. These are not symmetrically arranged in space. You've got this whole negative end of the molecule up here. That is also polar. Take away one and replace it with another. Now, look at this. You now have gone to a nonpolar structure. Your atoms are 180 degrees apart, separated by 3 120-degree lone pairs that are equally distributed in space, so your molecule is now nonpolar. So if we replace one of those lone pairs, seesaw was polar, T-shaped was polar, seesaw is polar, but trigonal bipyramidal is nonpolar. So it may take you a while of looking at this symmetry to determine that. But if you have lone pairs that are not equally organized in space, they aren't equal distances, or your atoms are not arranged symmetrically, then you are a polar molecule. Okay? So your job is to do the best you can with building these. I will be posting one more video after this that shows me building them, although I'm going to use a molecular model kit instead of the gumdrops, but hopefully you will get how to do this, and your whole work week is spent on completing this sheet.